Hi, I'm Baldwin Nsonga, and welcome to the presentation for Visualizing Similarity of Pathline Dynamics in 2D Flow Fields. The understanding of time-dependent flow fields is relevant to various application domains, such as climate research or engineering. Flow visualization can support experts by providing insight into data. This is especially challenging as time-dependent flow fields exhibit chaotic, unsteady dynamics. In addition, self-similar patterns in the form of vortices occur, which are multi-scale in space and time. Flow visualization research has mainly focused on the detection and depiction of various flow features, such as Lagrangian coherent structures or vortices. This is challenging as they require formal descriptions for a specific flow feature. We want to leverage the knowledge of domain experts as they have an intuition where in the domain specific flow features can be expected. We do this by utilizing the concept of similarity. Our goal is a fast, physics-based similarity visualization where the user can select a region and obtains a visualization of regions in which similar behavior is found in the data. First, what is similarity? We define similarity as a scalar quantity between two pathlines or two sets of pathlines. It should be based on physical quantities, allowing for an intuitive interpretation of the results by domain experts. Also, it should not depend on time, meaning that the similarity should not be affected by when two tracer particles exhibit similar physical quantities, as long as they do. Also, it should be symmetric. We found the Jensen-Shannon divergence to be suitable for this task. It is based on information theory and compares the similarity between two distributions. So, our method is based on first computing the dynamics distribution, which we then use to compute the Jensen-Shannon divergence. The first step, for every grid point, we compute a path line. We then split the path line into short time segments. For every time segment, we can compute the so-called infinitesimal strain tensor, which describes small deformations. We call this set of infinitesimal strain tensor a strain progression. We then take the set of the strains and compute the scalar quantity for each infinitesimal strain tensor. The scalar quantities strain and the rotation. We combine these two quantities into a dynamics distribution. In the second step, the user can select a region within the domain. Based on the selected region, we select distributions and combine these into a reference distribution. At every grid point, we can now compute the Jensen-Shannon divergence between the distribution of a specific path line and the reference distribution. We applied our method to two datasets. The first dataset is the von Karman vortex street. We have two use cases. In the first use case at the top, the user selects a region in which low dynamics are expected. So the user wants to see where dissimilar regions are, indicating anomalies. In the bottom image, you can see a user knowing there should be a vortex at that position, selecting the region, and the method displays in dark low divergence, meaning high similarity where other vortices are expected. This is consistent with our expectations. In the second example, we applied our method to a heated cylinder where buoyancy effects cause turbulence. Here we also have two use cases. The left use case corresponds to the first use case in the von Karman vortex street dataset. This dataset can be especially challenging as clutter can be expected due to the turbulence. So the user selects a wide region as shown in the right image. As a result, the general divergence increases overall. Nevertheless, significant vortices are successfully indicated by our method. Here we also tested the computation time. For the first step, it took around 13 seconds on a standard workstation to compute the dynamics distribution, and it took around 1 second to compute the Jensen-Shannon divergence from a user selection. This means a user can select a region and it takes 1 second to update the output. For this example, approximately 3 million allocations for scalar values were required. In conclusion, we proposed a user-guided method for the visualization of similarity and dissimilarity. The short computation time for the second step allows for an easy exploration of the dataset. In the future, we will extend this approach to three-dimensional flow. We will investigate clustering based on the dynamics distribution and our concept of similarity. And we will improve the memory efficiency, which is especially relevant when extending our approach to three-dimensional flows. Thank you for your attention.